Sorry?
You mentioned there's a discussant.
Yes. Right now, I will introduce the details to you, also to the audience in this Zoom room.
Okay.
So let me start it. So hello, everyone. Welcome to this Young Achiever Seminar. So my name is Wenbo Zhang, a second-year PhD student in ISD Penn State. In this semester, I'm helping the Center for Socially Responsible Artificial Intelligence to organize this talk series. So today is our third talk. We are happy to have Lily Xu, a senior PhD student from Harvard University, to share her research related to AI for social impact. So her research focuses on advancing AI methods in machine learning and game theory to address the wildlife conservation through poaching prevention. So let me make a short introduction. For today's talk, we will have two parts. In the first session, so Lily will share her talk at first, and then in second part, we will have about 5 to 10 minutes QA session. And we will have two discussants to lead this discussion. So shall we start, Lily?
I'm happy to.
Sure.
Okay, well, thank you so much, Wenbo, for the kind introduction. Thanks to you and Amelia for organizing the series. Thank you, Dr. Sundar, for organizing the center, and to all of you for tuning in. So I'm going to be presenting an overview of my work, which is developing methods in online learning and sequential decision-making in the face of uncertainty with motivations for wildlife conservation. So the high-level motivation of my work is that of the biodiversity crisis. So as recently as a century ago, populations of keystone species such as rhinos, tigers, and elephants were fairly robust. But today, these numbers have dropped over 96% for each of these species, and all of these key animals are in danger of extinction. And in fact, worldwide, of the 8 million species on this planet, 1 million species are in danger of extinction in the coming decades, according to a recent international panel. So this is a really, really urgent issue, and the United Nations has urged that the broader scientific and community and society overall treat the biodiversity crisis with as much urgency as we are treating the climate crisis. So one of the primary threats to biodiversity is illegal wildlife poaching, second only to habitat loss. And wildlife poaching happens mostly in the form of passive hunting techniques, such as snares. So in this photo, we have a wire snare that has been set up between two trees, placed on a game trail. So a common place where animals will walk, perhaps to find a watering hole or go to a food source. And as the animal walks through this path, its head will be caught in this wire snare. It'll tighten up like a noose, and the animal will be stuck there until the poacher comes back a few days or so later and collects its catch. So it's a huge threat to biodiversity. And unfortunately, snares are also indiscriminate. So even if a poacher is out there trying to hunt for bushmeat like deer or a pig, it could inadvertently catch an endangered leopard, for example, instead. So one of the most prime methods of preventing poaching is that rangers will go through protected areas, looking for as many of these snares as possible and removing them so they're no longer around to trap animals. So on the left, we have a bunch of snares that rangers have removed in Cambodia. These are specifically large traps meant to catch elephants. And as rangers go on patrols, they'll carry GPS trackers to record where they've been and where they found illegal activity. So that becomes the input data that we use for our later models. So to give a broad overview of my work and what I'll present today, all of my research focuses on this pipeline where we're going from data, such as that from our ranger patrol observations, and build algorithmic models and bring it all the way to deployment. So oftentimes in a first step, there is machine learning to try to estimate what these broader patterns are. So where are poachers going? Where are the snares most commonly in the park? Using that information to do some kind of planning, often sequential decision-making, such as with reinforcement learning. Then actually evaluating our approaches in conversation with rangers and conservation experts. And then finally deploying our work on the ground so that it can be used to protect animals. So In today's talk, I'll focus on a subset of the research that I've done so far. And the broader message that I want to emphasize is that if we want to achieve real-world conservation impact, which I think is really aligned with the goals of CSRAI, we have to really focus on addressing real-world constraints. And some of the real-world constraints that we see in physical settings, such as environmental planning and biodiversity conservation, are, for example, a short planning horizon and a lot of uncertainty about the environment. And this stands in contrast with the settings in which techniques like online learning and reinforcement learning are most commonly used, which are for things like recommender systems and robotics. We have a lot more plentiful data, there's a lot more precision, and also it's a lower stakes environment. So if we mess up a little bit, or if we take a little bit longer to converge, it doesn't really make that much of an impact on the ground. But for the setting that we're considering, any additional time that we're waiting, any imprecision that we have with our environment modeling will lead to animal lives lost. So with that, I'll go in with a case study, and then also just say that if any questions come up throughout, I'm happy to keep this conversational. So please do feel free to ask questions as we go along. Okay. So I'll start off with introducing our case study, which is a park that I've had the pleasure of working really closely with throughout the course of my PhD, and that is Sripak Wildlife Sanctuary, which is a large protected area in Cambodia. On the eastern boundary of Cambodia, adjacent with Vietnam. So Sripak is a very, very large park, nearly 4,000 square kilometers, which is about the size of Rhode Island. And for this entire park, they only have 72 rangers to patrol the entire space. So you can kind of imagine 72 rangers going through a forest the size of Rhode Island. It's a really, really hard problem if they're looking for small wire snares. And there are a lot of places that they've never been or have not been to in many years. And to get a sense of what's at stake, Sripak is home to a diverse population of animals, including keystone species such as elephants, muntjac, which are a barking deer, bangtang, which are a wild cow, which are poached for their horns, and pigs, which are poached for bushmeat. So all of these animals are targeted by poachers. And then the data that we have from Sripak about the patterns in this park and past poaching observations come from these ranger observations that are recorded by their GPS trackers. So, for example, in 6 years of patrol in Sripak, I've visualized on this map, a single little brown dot is one GPS waypoint. So one of these observations, for example, might note biodiversity observations such as elephant tracks, poaching activities such as snares, or an illegal campsite. But just looking at this map, you can probably tell that the distribution of ranger patrols is not even throughout the park. So you can probably guess without any additional information where the roads are in this protected area or where the patrol posts are that rangers are starting and stopping every patrol. So our historical data is really biased, and there's also a lot of places that rangers just aren't going to at all, even in 6 years of patrol. So every place that's still left in green, rangers have not been to a single time in the past 6 years. So there could be a lot of poaching that's happening there. We're just missing out on it. Yeah. So what we do is take those historical patrol observations, and to prepare it for a machine learning model, we begin by discretizing the park into 1 square kilometer regions. So each one of these pixels is a 1 by 1 square kilometer area of the park, and the dark blue areas indicate the places where historically rangers have exerted more effort, where we measure effort in terms of kilometers patrolled in a given month. And we can also isolate out all of the past observations of poaching activity. So each one of these red dots, for example, is an observation of a snare. And then if what we input into our machine learning model are all the covariates that we think might be correlated with poaching risk. So we have landscape features such as where the rivers are, what the land cover is, animal density. We have human features such as where the roads are and villages and patrol posts. And we also have a lot of temporal information such as temperature, precipitation, and vegetation that changes on a month-to-month basis. So all of these become inputs into our machine learning model. And I won't go into the details here, but some of the considerations that we have to account for when developing a supervised learning process here is very stark class imbalance. So for each place that rangers have been, there's a class imbalance of about 1 to 200. So for every positive label where we're finding snares, there are 199 cases in which we don't find snares. So there's very stark class imbalance. And there's also imperfect detection. So if we find a snare, we know that there was a snare there, but if we have a negative label, it's uncertain. So these are some of the challenges that we have to overcome. And we have an ensemble process that goes through those challenges. But overall, we take this information and we generate predictive maps where the bright red areas in this map indicate the areas where we think poaching is most likely to occur, and then light indicates less poaching threat. And we have 3 different maps visualized here: an overall map, and then separate ones for the dry season and the rainy season, because in conversations with park managers here, they've pointed out that Shripok experiences really strong seasonality. So in the rainy season, some of the rivers will flood over and become impermeable, so you just can't really cross it, and that really changes the accessibility of different parts of the park. Whereas in the dry season, those rivers will dry up, so you can easily cross through. So you'll also notice, for example, in the predictive maps that we have, some of the areas where we're predicting the highest poaching threat, such as the northeast corner, if you look at the historical effort, rangers haven't really been there at all, even in the course of those 6 years. So when we were first developing this, I looked at this and said, hey, we must be missing out on something. There must be something we're like not adding into our model, because otherwise, why would rangers not be patrolling that northeast corner? So I asked the folks there, and they said, the reason we haven't been patrolling there is because, as you might recall, Shripok is on the eastern boundary of Cambodia, adjacent with Vietnam. So it's actually an international boundary that's on that eastern side. So there's already international border patrol that patrols that 5-kilometer region. So Ranger said, okay, there's no need to patrol there because it's already being patrolled. But then when we were deploying field tests, we had rangers, but we picked one of those areas in that northeast corner for rangers to patrol. And they ended up finding a bunch of elephant traps there. And what it turns out to be the case was that international poachers were coming from across the international boundary. And those are typically the demographic that are like looking for big valuable game, such as elephant ivory, and placing a bunch of traps there. So these were areas that were previously completely missed out on by the rangers. So we were really excited that we were able to kind of like show them these insights. But after we built up this supervised learning model, we wanted to evaluate how well this performs, aside from just measures like AUC and precision recall. So we implemented a series of month-long field tests in Cambodia, where we picked 15 areas throughout the park. So 5 of which our model predicted to be at high risk of poaching, 5 at medium risk of poaching, and 5 at low risk of poaching. And to keep this a more valid experiment, we ensured that all of these areas were infrequently patrolled in the past, so we weren't just relying on historical patterns. And also that we kept it a blind experiment by not informing the rangers of the relative risk prediction of each of these areas. So on the right here is a photo of rangers coming back from a 4-day patrol with all of these rolls of wire snares that they removed from the park, along with 3 chainsaws that they confiscated from illegal loggers. But then when we got the data back from the rangers after these month-long patrols, we analyzed it and compared it to our risk predictions. And what we found is that the rangers ended up finding many more snares, normalized by the amount of effort that they were exerting in the areas that we predicted to be at high risk than in the medium risk areas. And they found almost none in the low risk areas, which showed to us that our model was really able to effectively discriminate between poaching threat. And then in a subsequent month, when we were focused on high risk areas, the rangers found over 1,000 snares. I appreciate the heart. Yeah, fine. The rangers found over 1,000 snares in a single month, which compares to a typical month where they would only find between 200 and 500 snares. So we were really excited about this outcome. And we were more excited to get this feedback from our partners at WWF, where Rohit Singh, the head of the Zero Poaching Initiative, mentioned that I am super excited with the results. Let's get this going in other countries too this year. So this very exciting email, we have expanded our partnership beyond just WWF to a broader consortium of conservation organizations that form this coalition called SMART. And one of the initiatives that SMART has is a software system called the Spatial Monitoring and Reporting Tool. So this SMART software is a broadly used tool for protected area management, where right now it enables rangers to like record, manage, and visualize their patrols, but there's no predictive component or prescriptive component. So that's where we've come in to fill the gap by integrating our predictive model, this PAWS AI system, so that we can directly take the data that rangers are already collecting on SMART, and then enabling them to just kind of click a button on this software and run our models and then generate these predictions on their own. So trying to kind of meet them where they are in the places where they're already collecting data to make this as frictionless a process as possible. And SMART is widely used in protected areas around the world. So that makes our PAWS system, therefore, also available to all thousands of protected areas that are using the SMART system. But some of the on SMART are similar to SHPOC, where they have a lot of historical patrol records, many years of data, and we can use this to make reasonable estimates of poaching risk. But there are other parts of the SMART platform, such as Royal Baloum State Park in Malaysia, that are only just beginning to use SMART and start recording their patrols. So we were actually talking with Royal Baloum, and we're walking through some of the results from deployment in Cambodia. And they were really excited about this and said, hey, we would love to partner with you. Can you make predictions for us? And we said, yes, we'd be happy to. But when they sent us their data, this is what we saw. They had only 3 months of patrols. Over half of the park had never been patrolled at all. So it was really just too little information to build anything useful. But this challenge indicated to us what we should focus on next as AI researchers. So that leads us to what I call the dual mandate, where for data-rich parks, we can use that historical patrol data to build predictive models for patrol planning. But then for data-scarce parks, such as Royal Baloum, we have to proactively conduct patrols that simultaneously detect poaching activity while also improving the predictive model. So detecting poaching activity from the historical data requires that we exploit historical patterns, and improving the predictive model requires that we explore areas with a lot of uncertainty. So this really parallels the exploration-exploitation trade-off that is the paradigm of online learning, which led us to take an approach with multi-armed bandits. So to just go into our multi-armed bandit approach, I'll begin by taking this abstract representation of a park. So here we have a protected area with n targets, each with an associated feature vector. So each of those feature vectors would be the covariates that we were seeing earlier, such as land cover, distance to road, and so on. And our objective is to help rangers plan patrols by having some allocation of patrol effort, which we'll describe as this vector beta, subject to a budget constraint B. So each component of beta will tell us for target I, how many kilometers should we be patrolling in that region. And I want to point out that we're thinking about patrol effort, not just in terms of like where we're patrolling, but also how much time we're spending in each area. Because when we were looking at the data from SHPOC, we saw that the more distance that the rangers patrolled, the greater the probability was of them finding a snare. So we have this kind of like monotonically increasing effect, but then also there's actually diminishing returns. So we don't want to just spend too much time in any one area. There's kind of this sweet spot where we'd want to spend that excess time patrolling a different area. So it's really important to consider not just where we patrol, but how much time we spend in each location, if we really want to maximize efficacy. Various things I'll point out about the shape of these poaching patterns, which I'll call each of these are reward functions. So our reward we think of as the likelihood of us finding a snare. So first we have that these functions are monotonically non-decreasing. Second, we have that they're relatively smooth, so we can call them Lipschitz continuous with some Lipschitz constant L. And then third, we also have that if we exert zero amount of patrol, we have zero probability of finding a snare. And this seems really trivial, but we'll show later on how that is actually helpful. So to apply online learning, to take a multi-armed bandit approach here, there are various challenges with this environmental domain that prevent us from directly using out-of-the-box techniques. So first, we have a combinatorial action space. And not only do we have to pick some subset K of these end targets, but actually we also have to consider how many kilometers of patrol do we want to spend at each target? How much effort do we want to exert? So this becomes an exponential problem space. And technically, also, our set of actions is continuous because the distance that we're spending patrolling could be any real valued number between, let's say, like 0 and 20 kilometers of patrol. So that makes our action space, now infinitely large. And additionally, because we're in this kind of like high stakes real world setting, we really want to minimize short-term losses because typically multi-armed bandit algorithms are evaluated in terms of their convergence at an asymptotic rate. So, as we go into infinite number of time steps, how well are we performing? Are we achieving zero? Are we achieving no regret? But in the critical real world setting that we're considering, the longer that we wait, the more animals are being poached. So we really want to ensure that we're performing well in the short term as well, not just the long term. So to overcome these challenges, we'll leverage the structure in the reward function that we were just looking at to reduce the amount of exploration that we have to do so that we can more effectively exploit and therefore achieve higher reward faster. And then also we are able to warm start our algorithm with the little bit of historical data that we have. Okay, so I'll just really briefly introduce the intuition behind many multi-armed bandit algorithms for any folks in the audience who aren't familiar. So multi-armed bandit algorithms think about how to optimally select one action. So if you have two actions that we're considering, A and B, let's say that we've played each action a number of times and we have an average reward of 0.5 for each of these actions. So they seem, like A and B are pretty equal. We don't really care which one we pick. But if we also keep track of a confidence interval over these, just depending on the number of times that we've pulled each action, then the more times that we pull one action here, we pulled action B more times, we're more confident about our estimate of what the true expected reward of B is compared to A, which has higher variance. So multi-armed bandit algorithms will oftentimes use a principle called optimism in the face of uncertainty, where we'll take the upper confidence bound, the UCB of each action, and then use that as our decision at each time step. And the intuition there being that at each time step, either we have the possibility of achieving really high reward, or we'll go to an area with a lot of uncertainty in which we'll take steps to improve our model faster. And even if the empirical reward of A were lower than that of B, we would still prefer to take action A as long as the UCB is higher than that of B. So we'd play action A, that would shrink our confidence radius, and we'd continue to play A until the confidence radius, the UCB of A, is lower than that of B. So this is the fundamental approach, the UCB approach that we'll build off of. And then to enable our objective of achieving higher reward in a short time horizon, we'll first leverage the fact that we have decomposability in our action space. So as mentioned, one of our key challenges is that we have an exponential number of arms. So for every single one of the end targets, we have to pick how much effort we're going to exert there. So if we have n targets and m effort levels, we have m to the n possible actions that we have to choose from. So the approach that we consider is that we track the rewards separately because our action is actually decomposable. So the reward, the total number of snares that we get for taking one patrol, can be broken down into how much effort do we spend at each one of the end targets separately, and did we find a snare there or not. So by tracking the reward of each target at each level of effort separately, then we reduce our exponential action space from m to the n to a linear m times n number of things that we have to track. And to give an example of what this looks like, if we have, let's say we have we consider each target at one of 5 discrete levels of effort, so between 1 to 5 kilometers of patrol. And if we have 4 targets total, then our total, the total number of things that we have to track are 20, 4 times 5. But if we zoom in on one of these targets more specifically, we'd recognize that if we have a good estimate for the expected reward at 4 kilometers of patrol, for example, that gives us a reasonable estimate of what the possible reward would be at any other level of effort at this target. So these are all things that we can do to improve our learning. So what that would look like is, let's suppose here A and B actually represent our empirical reward at target 1 for 2 different levels of effort. A is at 1 kilometer of effort and B is at 3 kilometers of effort. So if we've only played one of these 2 actions, then the possibility for the reward of any level of effort other than exactly 1 and 3 could be anywhere in this green range. So like the naive bandit approach would be that we'd have to do exploration in all of this green area, which would take a long time to kind of shrink down all of those confidence radii. So here's where we bring in the structure of our reward function to improve our learning. So first, if we consider Lipschitz continuity, that says for any level of effort, the change in the potential reward can only differ by a maximum of some Lipschitz constant L. So that Lipschitz continuity assumption will therefore prune down our uncertainty space so that we don't have to bother exploring any of that green region we just cut out. It simplifies our learning. And then we also have the fact that at 0 kilometers of patrol, we don't expect to find snares at all. So this 0 by equals 0 assumption, which seems really trivial, when combined with our smoothness assumption, actually is also extremely helpful in reducing our uncertainty. And finally, we bring in monotonicity, where as we increase the amount of effort that we spend, we're never going to be less likely of finding a snare. So monotonicity as well also improves our learning. So we've now kind of reduced the amount of exploration that we have to do from that entire green region and simplified it quite considerably for this one target. But now, if we go back to the broader picture, so we just kind of simplified our reward estimates for target 1. But if we have a good estimate for the reward of target 1, that gives us some understanding of what the reward for the rest of the park would be as well, because recall that these aren't arms that are just kind of like living in isolation, but rather they actually correspond with like a physical place in the real world, like actually a location in this park. So if we have a good estimate of the reward at target 1, all of our assumptions actually applies across targets as well. So if we consider target 2, where we've never explored yet before, we have no idea what the patterns are like there. So then when we start with, all we have is the 0 equals 0 assumption. But if we look at the similarity between targets 1 and 2, so let's say its feature set contains only elevation, and its elevation differs by like 100 meters. So then the delta difference between 1 and 2, when combined with our Lipschitz continuity assumption, enables us to transfer our learning from target 1 over to target 2, which will then further simplify our uncertainty and the amount that we have to explore. So all of these processes give us an estimate for the possible reward, the upper confidence bound, at each of those m times n levels of effort for each target. So then now that we have those estimates of the upper confidence bound for each of those values, we have an oracle, which we instantiate with a mathematical program that actually chooses our combinatory action, which is this vector beta. So we choose beta by maximizing our objective of the total UCB values for each of the subcomponents that we select, subject to a budget constraint B. And overall, this approach we call the lizard algorithm, which stands for Lipschitz arms with reward decomposition, which integrates all of these domain insights from the environmental space of decomposability, Lipschitz continuity, monotonicity, and historical data to more effectively do online learning in this setting. And I want to highlight that the integration of these ideas actually leads to improved theoretical bounds as well. So if we have n targets, some Lipschitz constant L, and a time horizon of t, the regret that lizard incurs is as follows. And traditionally, in multi-arm bandit algorithms, the time horizon dominates all other factors. So this would really be of the order t to the 2/3. And this compares to existing regret bounds for Lipschitz bandits from Kleinberg et al. In 2019, where they actually prove that a lower bound for Lipschitz bandits without the combinatorial aspect that we introduce is t to the n+1 over n+2. So that means anytime n is greater than 1, we improve in regret for all of those values. So we're able to, by combining decomposability along with monotonicity and Lipschitz continuity, we're actually able to improve upon theoretical bounds as well. We're also achieving strong empirical performance. So here we have simulations from real poaching data from Sripak, in which the performance of our lizard algorithm in green achieves the highest performance compared to existing bandit baselines. And I want to highlight this is in particular in the early time steps, which is what we truly care about in this setting. To quickly describe some follow-up work that we have from this approach. We've also considered, well, what if we want to do online learning and plan patrols in a setting where we're actually considering our overall objective, which is that of wildlife conservation. So if we consider a protected area with 5 regions, let's suppose that each one of these areas, has some poaching probability that we describe as mu I. Our ultimate goal is to conserve the most endangered species. So we'd recognize that in the real world, the areas where the most endangered species are, such as elephants, might not correspond with the areas that there's greatest poaching threat. Because, for example, many of the poachers are bushmeat poachers that are looking for deer rather than endangered elephants. So here, the locations, targets 1 and 2, for example, where there's the greatest risk of poaching, don't correspond with the areas where there's the most vulnerable species. So we have follow-up work from Ishkai that is actually directly integrating these kinds of species prioritization constraints in our objective so that we can do this trade-off between maximizing reward, which is to remove as many snares as possible, while also ensuring that we're meeting our ultimate objective, which is species conservation. And then all of the work that I've described so far has focused on a somewhat static setting in which we're trying to estimate the general risk of poaching at each area in the park. But a natural question to ask is that if we start patrolling one area really effectively and removing a lot of snares, the savvy poacher probably won't go back to the area. So they'll probably move somewhere else. So this question of how do poachers respond to our patrols has been a long-standing question and might require sequential planning. So to analyze this, to kind of understand poachers' behavior, we studied patrol data from 2 protected areas in Uganda, Murchison Falls and Queen Elizabeth National Park. And what we found is that when rangers patrol more in a 1 square kilometer region in a single month, the probability of poaching in the next time step actually goes down, which shows that there's a deterrence effect. So rangers actually are able to change poachers' behavior. We actually are able to deter them. So this deterrence necessitates sequential planning because our actions today actually change the state of the world tomorrow. So now we have to figure out not just where should we go that maximizes poaching threat, but what is a sequential policy that we have to consider. However, if we want to use a technique like reinforcement learning, we'd have to model the environment with some simulator. So you have to, define our model and learn estimates of all these parameters. But if we're trying to quantify, for example, the strength of the deterrence effect, we can estimate based on historical data that this effect might, have some coefficient 0.17. But because our historical data is imperfect, and we have a limited amount of it, we can't be too confident in this value. So instead, we might be much more confident of giving some interval in which this parameter might lie. So we might say that it's somewhere between 0.12 and 0.23. We're just not sure exactly what. So the fact that we have uncertainty in these environment parameters necessitates robust planning in which we are executing sequential decision-making in a way that we are robust to this interval uncertainty in our environment parameters that we call omega. So our approach from UAI 2021 introduces a framework that we call mirror, which enables robust planning with reinforcement learning by considering a minimax regret objective, which is much less conservative than the standard robustness notion of max-min reward, which is the norm in reinforcement learning. And to optimize for this really complex objective, we use an approach called double oracle, which sets up the problem, this min-max objective, as a zero-sum game between a planner who is learning an optimal policy and nature, which is our adversary that is trying to pick instantiations of these uncertain parameters to make the regret for the planner as bad as possible. And then we have an iterative process where we build up finite strategy spaces. We sample strategies for each of the planner and nature and iteratively grow this game until we reach convergence to an what we prove to be an epsilon optimal strategy in a finite number of time steps. Okay, so then after we considered this question of how are poachers responding to ranger patrols, and we built up this reinforcement learning framework, we kind of had this like nagging question in our head of like, can we show this this reaction a little bit more robustly? And the question of how poachers are actually responding to ranger patrols has never really been conclusively answered, even in conservation literature as well. So there's never been any kind of causal evidence for deterrence. So key challenge with getting at causation is that typically causation would require something like randomized controlled trials. But in high stakes settings, such as environmental conservation, causation is not possible because, or sorry, RCTs are not possible because they're very expensive to carry out, but also the opportunity cost is too high. So if we left an area, for example, that completely unpatrolled, then that means that area will be extremely vulnerable to poaching and other threats. So we just can't afford to do so. But additionally, we also have an unobserved outcome variable. So if we recall that it's really hard to like find snares in a park, you know, if you're just passing by, you might miss the small wire snare. So if we patrol an area and we find a snare, we know for a fact that there was a snare there. But if we don't find a snare, we can't be confident that there wasn't a snare there. We might have just missed out on it. So the uncertainty in our negative labels makes it really hard to get at a causal estimate as well, because we don't really know the true outcomes of what happens when we patrol, you know, like if we say, oh yeah, we patrolled and then poachers were deterred because we didn't see them the next stage, it might have been that we just missed out on it. So kind of disentangling detection, whether or not we detected a snare from the true presence of whether a snare was there is another critical challenge in this setting. So these two challenges, trying to overcome the fact that we can't conduct an RCT and overcoming the unobserved outcome variables are the two key challenges that we overcome in this work that is in preparation for submission soon. So the key idea behind our approach is that we leverage a historical field study as a quasi-experimental setting. So in fact, we consider a 2018 field test that was trying to evaluate the quality of the PAWS predictions. So just the same as the field test in Shupak that I was describing earlier when we had the high, medium, and low risk areas for rangers to patrol. So this field study that was executed over 5 months in 2018 changed the normal patterns of ranger patrols. So this introduced a shock to the system that helps overcome unobserved confounders. So visualized in this map, we have the change in patrol effort, where 0, this white area, is like areas that were patrolled kind of as expected, whatever baseline levels. So then we can use this to kind of simulate a randomized control trial where all the areas during the shock period that were patrolled less, we consider to be candidate control sites, and all the sites that were patrolled a lot more, we consider to be candidate treated sites. And then we use a process from causal inference called matching, along with other techniques from machine learning to kind of create estimates of ensuring that our treated controlled sites are actually very, very similar and account for as many possible confounders as possible to bring us to the first causal estimate of deterrence. And what we estimate is that we have a coefficient for how much poaching patterns will change as a function of the increase in ranger patrol. So anything that will be in the negative range indicates deterrence. So ideally, we want a coefficient in the negative range. And what we find is that this coefficient estimate to be negative 0.711 on a log odd scale. And this is actually fully within the negative range, which shows that this is actually a robust estimate indicating deterrence. And if we were to visualize the deterrence effect for each of the 4,000 sites in Murchison Falls, each one of these curves estimates the poaching probability of one site as a function of how much our patrol either increases or decreases from historical patterns. So if we were to look at the median line in this map, for example, at a baseline level of patrol, where we're patrolling kind of as business as usual, the probability of poaching is 21%. But then if we patrol 1 additional kilometer more, then this probability of poaching goes down to 12%, which is actually a 45% reduction in the probability of poaching, which is the first causal estimate of deterrence. So we're really excited about this, and we're hopeful that these insights will be valuable to the conservation world in trying to justify additional funding for rangers, the expansion of protected areas, as well as lead to more robust adversarial models for the computer science and game theory community as well. But to zoom out, so a high-level overview of my work from a deployment standpoint is all focused on AI for conservation impact through the PAWS system, which has involved close collaboration with conservation NGOs to really understand their problems and the constraints that they have, executing field tests in Cambodia and Uganda to ensure that the approaches that we propose are actually feasible on the ground, and then scaling up our impact through global deployment on existing conservation software such as SMART. So our integration with SMART has led to PAWS being deployed and used throughout Central America, Africa, and Southeast Asia, where we've been lucky to work with a large number of different conservation organizations. And most recently, we visited Rio Bravo Conservation Management Area in Belize and conducted a 4-day workshop and went on patrols with the rangers to really understand kind of what the landscape looks like, how the rangers respond to these predictions, how they make their patrol planning decisions, and whatnot. So this is like a really informative and immersive experience in getting more integrated into the setting. But at the same time, all of this has led to new developments from an AI perspective as well, where the more extensive conversations that we have with the domain experts has unearthed new exciting challenges that the existing AI literature, such as multi-armed bandits, weren't effectively considering. So each one of these has led to a contribution for the AI community, but is all kind of grounded in these conservation problems. So to kind of give an overview of some of these challenges for deploying AI in the real world, oftentimes we have insufficient data, which will require approaches like online learning. There might be a changing environment, which requires sequential planning. And also, we might have some different vulnerability in our species. So trying to prioritize that leads to new objective functions. And if we have uncertainty in the outcomes and we're trying to get some causal estimate, we have to really integrate causal inference with machine learning. So at a high level, I want to emphasize that AI has a lot to learn from conservation and other real world challenges. And I encourage you all, and I'm sure many of you at CSRI are already doing this, to really get more immersed in these kinds of domains to learn from these real world challenges. And to just close off, I'll share some of the lessons that I've learned from this kind of work in AI for social impact. And to just kind of highlight two of them. One is that it's really valuable to focus on incremental deployment before ambitious project design. So you notice in the work that I presented today, we started from like the most simple setting possible, which is just supervised learning, like pretty vanilla. But really executed field tests there and tested and evaluated things to make sure that the assumptions that we were making were reasonable, that we really understood the domain and the data that we had before moving on to online learning and then sequential decision making with RL. So really kind of getting things right before scaling up. And then also recognizing that real world constraints serve as research challenges and not just limitations. So whenever we had, when we were working with Loom State Park, for example, and they said, hey, we don't have a lot of data. At first we said, oh, shoot. And then we said, okay, well, that tells us what we should be working on next. So we should really focus on adapting our problems and our solutions for parks that don't have very much data. So that was kind of pointing us to the next priority area that we should address as researchers. So that's what I have to share, this work on AI for conservation. Thanks so much for your time and for, again, hosting this series. Here's how to find me online on Twitter or my website. And I want to just close by thanking all of my collaborators on the work that I presented today, as well as all of our many conservation partners who are doing the really important work on the ground. Thanks so much.
Okay, thanks for Lily's talk. So let's move to our QA session. Today we have Tingting and Yiren as our discussant. So shall we start with Tingting?
Hello, Lily and Wenbo. I'm Tingting. Thank you for your sharing today. Your research is really interesting. And especially this project, I really think it's great that we can use technologies and like artificial intelligence to solve practical problems. It's really great. So I noticed that you mentioned that the data you have is actually like biased and imbalanced. I'm interested in how you deal with this problem. Will you build the prediction model?
So there is a lot of bias in the data. We use a lot of like imbalanced data techniques, such as there's SMOT, so you can oversample the positive labels as to get a little bit of better balance. And there's also specific like domain inspired data augmentation that we do. So that key idea there's using the amount of patrol effort as a proxy for the reliability for negative labels. So we'll recognize that if we didn't find a snare at like 1 kilometer of patrol, we can't be very confident that there was not actually a snare there because maybe we just didn't patrol enough. But if we, didn't find a snare at 10 kilometers of patrol effort, then it's much more likely that there actually wasn't a snare there. So what that indicates to us is that anytime that we've patrolled, for example, 4 kilometers of patrol and we didn't find a snare, we also wouldn't have found a snare at 3 kilometers or 2 kilometers or whatnot. So we can do data augmentation by kind of like sampling those different values. And then on the flip side, when we're looking at positive labels, if we found a snare at 6 kilometers of patrol, we also would have found it at 7 kilometers of patrol and 8 kilometers of patrol and 9.2 kilometers of patrol. So we can do very specific data augmentation that makes our models more robust, can introduce more positive labels, but then also help out with the class imbalance.
Thank you. And I have another quick question. So I was thinking if it's possible to extend your system or your algorithm to other like domain, except for the the wild animal protection area. Do you have any like suggestions or comment on this question?
So I think there's a lot of other natural extensions if you just like move within the realm of environmental management. So things like addressing illegal logging or illegal fishing can be pretty like addressed out of the box with these techniques. Then there's also other kind of real world approaches that have a lot of similar challenges, like a lot of uncertainty and a lot of imperfections in the data. So for example, a lot of these techniques we've actually extended to public health settings as well. And that is kind of like another portion of my work that I had showed on that slide at the beginning, but didn't cover in this talk today, where we use a lot of the same like learning and planning techniques for maternal health care by leveraging historical data about how mothers will engage with an intervention program to get information about preventative healthcare, and then trying to figure out how can we schedule optimal interventions to these mothers in the face of limited data and a lot of uncertainty.
Yeah, thank you. Thank you for your sharing today.
How about Yiran?
Thank you, Ting Ting.
Yeah. So yeah, hi Lily. Thanks for sharing. I really love your work, and yeah, applying different models like targeting different real world scenarios is quite impressive. And I'm kind of interested in like I remember you like select 2 areas to evaluate the poachers deterrence activity or like the deterrence, right? So I'm kind of interested in why you like select these 2 areas to to evaluate their deterrence.
Are you talking about like the actual sites that we were working with, like Merced Falls and Queen Elizabeth?
Yeah, because yeah.
So the reason that we were
you talk.
Yeah, so the reason that we were working with, for example, Merced Falls, for the causal study that I was pointing to, is because of 2 things. One, we needed a place where there was some sort of historical shock that happened in order to get to come at a causal conclusion, because otherwise there would be too many unmeasured confounders that we wouldn't be able to account for. So the fact that there was actually a field test that was conducted in the past was a necessity to enable our causal inference. And it was really cool that we were able to, you know, leverage this field study that was executed 5 years ago for a totally different purpose, which is to evaluate the quality of a predictive machine learning system, and instead apply that to analyze this question of like how are rangers actually responding to how are poachers responding to ranger patrols. But then with that criteria of like, okay, we need a shock, then that means we had field tests that were executed in Merced Falls National Park in Uganda, and then also Sripak Wildlife Sanctuary in Cambodia. And the reason that we picked Merced Falls over Sripak is because the quality of the data in Merced Falls is just a lot better. So first of all, there's much less class imbalance to kind of get at the question that Ting Ting was asking about. So there's just more snares, there's more patrolling, there's more findings that are happening in Merced Falls. But then also there's just a larger array of data and more coverage because the patrols there are like just a little bit more well resourced. So it just leads to higher quality data than Sripak.
Yeah, I see. Thanks for answering. And the second question is like, how do you communicate with NGL to evaluate the models since they are not expert in AI?
So I think that thank you so much for asking that question, Yiran, and I think that's so important for this kind of work, and probably for a lot of the things that you all are working on at Penn State too. So I think a big part of my PhD has as important, as learning about regret bounds and like optimality and optimization and all of these things has been learning how to communicate and how to manage a project and how to, first like learn these technical ideas, but then learn how to communicate them to domain experts and people who, have no idea what how linear regression even works. So figuring out how to distill these kinds of like complex questions into really simple settings that are interpretable and intuitive by these people who have a lot of expertise in a very, very different domain, which is like conservation and executing challenges on the ground, is important. And it really has to be a two-way street. It has to be okay, like how do I describe how reinforcement learning works to a park ranger, but then how can I listen to them and understand like, okay, what are their constraints? What are their priorities? Like, oh, seasonality is something that really is important. Oh, you really care about like different species more than others, and you want to allocate your resources more effectively that way. To just kind of engaging these conversations and asking open-ended questions, and then always kind of like taking what they're saying and trying to translate that into something more like mathematical and implementable, is just this constant skills developing process that I think all of us as AI for social impact researchers undergo.
I see. So yeah, thanks for answering.
Okay, thank you for Lily's answer, especially for the experience related to how to communicate with the collaborator or the NGOs, because as in our group, we are also facing with how to communicate with our collaborators, how to tell them all the technical details to make sure they understand what we are doing. So thank you so much for sharing. So is there any other person have questions?
Yeah, actually, I do have some questions.
Sure, go ahead. Yeah.
Hello, I'm Yafeng. Actually, I'm not an AI researcher. I'm from HCI. So, but I think for HCI, it's more like how people, use technology and how do they use their technology. So, what like Iran just asked is a very interesting question, and I want to follow up that question. That if because you said that you have an evaluation workshop after they use that system, right? And I wonder, like, how do they react?
So the rangers were generally like really excited about this. They many of them are younger. In Rio Bravo, in Belize at least, many of them are younger. So like in their early 20s, for example, and they're really excited about technology. So even the fact that they like learned how to use this like the smarts tool on their phones and whatnot was kind of this like exciting like technical development for them. So the idea of like having AI systems and trying to understand like, okay, how, what is the data that we're collecting? How does that feed into some other system? How do I interpret these predictions? They were really interested in kind of like learning more about the process and the possibility of also kind of making their resources more effective, because the key challenge in all these parks, is that they have too much land to cover, too many poaching and logging threats occurring, and just dangers. And they're always kind of going through this like cat and mouse game of like, oh my gosh, where should we be going next? Like what should we be doing next month and whatnot. So the idea of having kind of a more structured way of helping with patrol planning and actually getting more concrete recommendations while leveraging the data that they're working on collecting was generally exciting to them.
So you have any like functions or features in the system, like interfaces, kind of tell them what how to make decisions about, because it's not only about planning, but also because it's kind of complex, like the species priority and game theory, whether the poachers will change according to their activity, right? Yeah, and then like how do you make them understand this, the suggestions, the recommendation routes, and so it's like explainability, I guess.
Yeah, that's a great question. And so the way that we are doing this kind of translation, at least for the first stage, is just focusing on this like visual depiction. So we just show them this map that you see on here, where like the dark red areas are the areas we think that there's more poaching threat, and we actually overlaid their historical ranger patrols, like all their waypoints, onto this map to kind of show this the discrepancy between where they were patrolling and where like the high risk poaching areas seemed to be, and just going through this kind of like collaborative process of saying, okay, well, it seems like we're predicting a lot of poaching threat here, but you haven't been there before, or like you haven't been there last month. Why is that? And that, you know, both led to them having the discussions about like, okay, well, you know, those areas are kind of like hard to access. Maybe we should try going there. While us also learning, oh wow, you know, there's a protected area kind of adjacent on the other side of this boundary, so it would be really hard for anyone to access this, or like the forest is super dense over here, so there's actually not much likelihood of poaching happening there. It was really this kind of this.
Oh, so it's more like you're showing information and they will reason like rationale. Yeah, they'll have their own rationale, like how to plan.
Exactly, yeah. But if you wanted to just kind of do like the most direct way, you would look at this map and say, okay, these are the areas that have the highest red. And you can, you know, you can convert all of these to numbers and then pick like, okay, these are like the top 10 areas that we want to focus on for the next month, for example. So that would kind of be like the most like actionable approach.
Is there any like issues when they are using these systems, like challenges using it?
I think challenges can mean a lot of different things.
Yeah, that's
like
true.
Like just engineering challenges, like understanding challenges.
The way because they are not going to use, you know, develop the system, I guess.
Yeah, definitely. So the way that we pitch our PAWS recommendations is purely that, as recommendations. So we're just trying to extrapolate to future patterns and to areas where they haven't patrolled very much, and make recommendations for, okay, these kind of seem to be priority areas that you might want to consider patrolling more in the next month or so. But we really want to have it not be we are prescribing an action to you, but rather we're making these recommendations, and then we want you to kind of like deliberate and then come on out with your expert knowledge to decide what action to ultimately take. Like, do you patrol this area that kind of PAWS recommended, or do you go about your normal patrol planning processes?
Okay, that's so cool. Yeah, because I feel like kind of understanding this domain experts or users is kind of like our work, and like we usually do like interviews or observations, understand them, and then kind of turn these findings into some design implications that kind of for the AI researchers to, you know, create a system. And I was wondering, like, if you have any suggestions for HI researchers, like what kind of findings or suggestions they are seeking for. Because one I hear from your talk is that you want to translate this complex constraints environments, practices into like simple or simplified methods or like explanations or insights that you can actually create a computational method to solve the process, the question. And I was wondering if there's any other similar suggestions.
Yeah, I love so much that you're asking these questions, because I really feel like the HCI community is one of those sub-communities in AI or in computer science that has been definitely the most thoughtful about kind of what problems to work on and how we should be interfacing with stakeholders and whatnot. So definitely we have so much to learn from you. But the one thing that has come up like again and again in our conversations with conservation partners is in explainability and interpretability. So even like, why is this area, you know, predicted to be more high risk than others? Like, we don't have a good answer for this. You know, there's kind of post hoc explainability, like heuristics we can use, but we aren't really able to give more kind of human intuition or human interpretable feedback from the outputs that we're generating from our models. And that is, I think, one of the most important next areas to focus on.
I see. Yeah, it's kind of cool because I'm also work on citizen science. I feel like not because these are actually also citizen scientists. I feel they're kind of collecting data and really, you know, implementing their strategies. And yeah, so I feel like your approaches can. That's why I say like probably like field-based citizen scientists can be one of your research users too. Okay, thank you for your sharing.
Yeah, I haven't worked with citizen science. Thank you, Yafan. I would love to discuss more.
Is there anyone has questions? Okay, so thanks again for Lily's talk. Before ending today's talk, I need to make an announcement for the next talk. For our next talk, we will have Christine from University of Maryland to share her research. Her research will focus on sequential decision-making and uncertainty, algorithmic fairness and knowledge representation and reasoning. So her talk will be held on April 6th. So if you're interested, please consider attending. So thanks again, everyone. So bye-bye.
Thanks so much,
Thank
Wenbo.
you.
Yeah,
Really appreciate it. Good to meet you all.
Thank you. Bye.